Okay, hello everyone in a new video. So we have reached part 4 of chapter 2, which is the chapter of electric voltage for grade 10 students. So in this part we are going to solve some exercises. Then let me start. Exercise number 10. The figure below shows an electric circuit. So they mentioned this figure, the electric circuit, now we can use it. Containing the following components: a DC generator, 6 lamps L1, L2, L3, L4, L5 and L6 such that L2 and L3 are identical. This is important. A voltmeter that indicates 6 volt. So let me label here the voltage. An oscilloscope with vertical sensitivity SV is equal to 6 volts per division connected across L6. And let me here write that the vertical sensitivity of this oscilloscope is given by SV is equal to 6 volts per division. Now given the switch K is closed, so now we close the switch, and we have that UBJ is equal to minus 4 volts. So let me write here. Then recall that the trick in solving such type of exercises is to write applied voltage on the electric circuit itself, but not only for the value but for the name of the voltage, and in this case is given by UBJ. Then number 1, they are telling me to determine the voltage UAB making use of the above diagram. So they mentioned they are talking about the second diagram. Now we can use it. So notice that the voltage UAB is being measured by the oscilloscope. So they are telling me already that the oscilloscope is measuring the voltage UAB, and this is because the phase terminal is connected to A and the mass terminal is connected to B. So no need to explain this, and let me write directly that the voltage measured by the oscilloscope is given by UAB is equal to SV multiplied by Y. So always in physics we need to write the formula that we are using. We cannot replace directly. Now SV in this case is given in the SI to be 6. What about the value of Y? Notice that the luminous line is, in this case, is displaced upward, so the value of Y is positive, and the number of divisions is given by 1, 2. So notice that in this case the unit of Y is given by division, simply because the vertical sensitivity is expressed in volts per division. Now plugging this on the calculator, then the value of UAB is given by 12 volt because everything in the SI, so UAB is equal to 12 volts. And let me write here that UAB is equal to 12 volts. Now in part 2, they are telling me to determine UHG. So the first thing that we must think about is the law of addition of voltages. So if we need to consider UHG, then in order to determine the voltage UHG, we can go from H to A to B, B back to J. Sorry, H to J and not HG, okay? But in this case, UAH is not given, okay? So, and if you consider all the possible cases and considering the law of addition of voltages, you can notice that this equation consists of two unknowns, UHJ in addition to another unknown. So for example, in this case it's given by HA. So here the law of addition of voltages is not beneficial, okay? But notice that here the voltmeter is indicating 6 volts. So it's measuring the voltage across the points H, J, because the voltmeter is connected in parallel across the terminals H and J. Then according to law of uniqueness of voltages, they have the same voltage. So, but now we need to explain whether the voltmeter measures UHG or UGH. So let me say, since the COM terminal is connected to J and the other terminal is connected to H, then the voltmeter measures U. Now, so the COM terminal corresponds for the second point here, which is J. So this is J, and the first point is given by H, which corresponds for the other terminal. Okay, so always the second point here corresponds for the COM. And indeed they are telling me to determine UHJ. Then in this case UHJ is equal to 6 volts. And here let me write that this is given by UHJ. Now in number 3 they are telling me to calculate UAH, and in this case we can use the law of addition of voltages. Then apply law of addition of voltages. Then always on the left we write the voltage that we are interested in calculating, which is given by UAH. And on the right hand side of this equation we go from A to H across different electric components such that we know their voltages. Then we will go from A to B, B to J, and J back to H, since we know all of these three voltages. Then UAB plus UBJ plus UJH. Now the value of UAB is given by 6, UBJ is given by -4, and if UHG is given by 6, then UGH is given by -6. Then in this case, let me check if there's something wrong. Okay, sorry, this is 12, yes. UAB is given by 12. Let me make it clear here. Then in this case 12 minus 6 minus 4 is given by 2. Since all of these quantities are expressed in the SI, so the value of UAH would be in the SI, which is false. So the potential difference or the voltage across the points A and H is given by 2 volts. So UAH is equal to 2 volts. Now in part 4 they are telling me to determine UHI. So we know UHJ to be 6 volt. In order to determine UHI we require to know UIJ, but notice that here in the given L2 and L3 are identical. Then let me say since L2 and L3 are identical, then they have the same voltage. Now mathematically, how do we formulate this statement that the lamps L2 and L3 have the same voltage? Notice that the voltage of the lamp L2 is given by UHI, which is equal to the voltage of the lamp L3, which is denoted by IJ. Now eliminating I, so this is equal to UHJ, which is the voltage across L2 and L3, divided by the number of electric components we have, which is 2. Then UHJ in this case is given by 6, divided by 2, so this is equal to 3. Since UHJ is expressed in volts, so the value of 3 will be in volts. Then in this case UHI is equal to 3 volts. Now in part 5 they are telling me that the J is taken as an electric potential reference. So notice that this terminal is different than that terminal. This terminal corresponds to the ground terminal of the oscilloscope, whereas this terminal corresponds for the electric potential reference. So they are telling me to calculate the potentials VH, VA, and VB. So first let's mention that the electric potential at the point J is 0 because it's taken as an electric potential reference. So electric potential at J, since J is taken as an electric potential reference, then we have that the electric potential at the point J is given by 0. Now we can consider these electric potentials. Now first let's determine VH. In order to determine the electric potential at the point H, we must know the voltage that relates this point into another point such that we know the electric potential at the other point. So if we consider the voltage UHG, let me say here electric potential at H. So UHG J is equal to 6 volts. Knowing that we are interested in determining VH, VH appears in this equation because UHG can be written as VH minus VJ, which is equal to 6. So let me complete this here. So VH minus VJ is equal to 6. Knowing that we are interested in determining VH, so the value of VJ is given by 0 and the reason is given by electric potential. So VH minus 0 is equal to 6. What's the type of this equation? Linear equation and one unknown. So the value of VH is equal to 6 volts in the SI because everything previously is expressed in the SI. And now let's move to the other point, which is given by VA, the electric potential at the point A. Then in order to determine the electric potential at the point A, we require that we know the voltage that relates this point to another point such that we know the electric potential at the other point. The closest one is the point H, and indeed we know the voltage at the point H, which is given by 6. Then if we write down that UAH is equal to 2 volts, which gives us that VA minus VH is equal to 2, knowing that we are interested in determining VA. Now the value of VH is given by 6. It's equal to 2. So what's the type of this equation? This is a linear equation and one unknown. The unknown is VA. Then VA is equal to 6 plus 2, which is equal to 8. Since everything is expressed in the SI, and then VA is expressed in the SI, which is volts. So VA is equal to 8 volts. Now finally we are interested in determining the electric potential at the point B. Now in order to determine the electric potential at the point B, we need to know the voltage that relates this point into another point such that we know the electric potential at the other point. Here we have three choices. We can consider the point A, we can consider the point N, and we can consider the point J. However, VB in this case is equal to Vn because between B and N we have a connecting wire. However, we don't know the electric potential at the point N. So we can consider A or J. So we know the voltage UBJ and we know the electric potential at the point J. Moreover, we know the electric potential at the point A and we know the voltage UAB. So let's consider the voltage UAB, which is given by 12 volts. Now this is given by VA minus VB, which is equal to 12, knowing that we are interested in determining VA. So VA, the value of VB, so VA is given by 8, VB is the unknown, we are interested in determining the electric potential at the point B. VA is given by 8 minus VB is equal to 12, so this is a linear equation and one unknown, the unknown is VB. Then dragging VB to the right hand side, it will be VB. Dragging 12 to the left hand side, it will be minus 12. Then in this case, VB is equal to 8 minus 12, which is equal to minus 4. Since both of these are expressed in volts, so VB will be expressed in volts. Now let's calculate the value of VB using another method. So let me here say or. If you consider the voltage UBJ to be minus 4 volts, which is VB minus VJ is equal to minus 4, we are interested in determining VB. Notice that J is taken as a reference electric potential, so this is 0, which is equal to minus 4. Then VB is equal to minus 4 volts. So independent of the choice that we are considering, these values must be equal, okay? So they are choice independent. Then we have reached exercise number 11. They are telling me 4 lamps are connected to a battery. Okay, 4 lamps are connected to a battery as shown in the adjacent figure. Then they mention this document. Now we can use it. Given that UPN is equal to 12 volts and UMB is equal to minus 8 volts. And as we have mentioned previously, that the trick in solving such type of exercises is to label the voltage across the electric circuit in addition to their names. So here we have that UPN is equal to 12 volts and UMB is equal to minus 8 volts. Now in number 1, they are telling me to calculate UBM. So notice that we have UMB is equal to minus 8 volts, and we know that whenever we flip these two letters, so we gain a minus sign, then UBM is equal to minus UMB. Now the value of UMB is given by minus 8, then it will be given by plus 8 volts. So UBM is equal to 8 volts. Now they are telling me to calculate UAB. Referring to this figure, we can see that UAB can be calculated using the law of addition of voltages, because from A to B we know all the voltages. Then let's say apply law of addition of voltages. Then always on the left we write the voltage that we are interested in calculating, which is UAB. And the trick is that to go from A to B across different electric components such that we know the voltages across them. So from A we will go to the point P. From P we will go to the point N. From N we will go to the point M, and from M back to B. Now across A and P we have a connecting wire, and we know that the voltage across a connecting wire is 0. Notice that we didn't justify this previously, so let me say between brackets that UAP is equal to 0, and the reason is given by a connecting wire. Now as for UPN is given to be 12. Now across N and M we have a connecting wire, so this is 0, and let me justify here that U and M is equal to 0, and the reason is given by a connecting wire. Now what about UMB? UMB is given by minus 8. So this is equal to 4. Since all of these quantities are expressed in the SI, which is volts, then UAB is equal to 4 volts. Therefore, let me label this voltage on this circuit. So UAB is equal to 4 volts. Now in number 2 they are telling me which terminal P or N has higher electric potential. So notice that here we can define the electric potential at the point P and the electric potential at the point N. When they tell me a higher electric potential, higher means greater. So we need, in other words, we need to determine which potentials VP or VN is greater. In other words, we need to compare between VP and VN. So this is maybe greater, less than, or equal. So we need to calculate Vp and Vn explicitly, but notice, or we need to know, but notice that we don't know the electric potentials at the point P and N because yet we didn't choose a reference electric potential on the electric circuit itself. However, this can be done in another way by considering the voltage UPN, because UPN is the value that relates Vp and Vn. Now in 2.1, let's say that UPN is equal to 12 volts. Vp and Vn are encoded in this equation, which is Vp minus Vn is equal to 12. Notice that 12 is a positive number, which means that Vp is greater, minus Vn is positive, which means that Vp is greater than Vn. So now we have compared between Vp and Vn, and let's say since Vp is greater than Vn, then the point P has higher electric potential and here it's important that to mention that we are comparing the point P to which point? To the point N. So compared to N. Now in 2.2, they are telling me which terminal B or M has a higher electric potential. Then admitting the same argument, we need to determine the voltage UBM or specify, which is given by, okay, so we have UMB. Let me say that UMB. Then we are interested in considering the voltage that relates to the points B and M, which is given by UMB, which is equal to minus 8 volts. So in this case, Vm minus Vb is equal to a negative number, which is negative, less than 0. Then in this case, we can say Vm minus Vb is negative, which means that Vm is less than Vb. So dragging Vb to the right hand side, and let me mention that's what's the type of this equation. This is an inequality between Vm and Vb. Now in this case, let me say since the potential at the point B is greater than the potential at the point M, then we can safely say then the point M has, then the point B has higher electric potential compared to which point? Compared to M. So this is important because at any point on this electric circuit, we can define an electric potential and we can compare it to any other point. So it's important that we need to mention between which points this comparison is being done. Okay, now in 2.3, they are telling me which terminal A or B has higher electric potential, and admitting the same argument in order to compare the potentials between A and B, knowing that we don't know the explicit values of VA and VP, we are interested in the voltage that relates these 2 points, which is given by UAB. So here we have that UAB is equal to 4 volts. Then VA and VB are encoded in this equation, which is equal to 4, knowing that 4 is a positive number. So it is VA minus VB, which is positive. This is given by VA greater than VB. Dragging VB to the right hand side, it will gain a minus sign, so it will be VA greater than VB. And let me say since VA is greater than VB, then the point A has higher electric potential compared to which point? Compared to B. Now in number 3, they are telling me that M is taken as an electric potential reference, and as shown here that this is the electric potential reference. Then we are interested in determining or calculating Vm, Vb, Va, Vp, the electric potentials at the points M, B, A, and P respectively. Then let's start by the electric potential at the point M. And let me say that since M is taken as an electric potential reference, then in this case the electric potential at the point M is given by 0. Notice that here I didn't include any unit for the 0 because anything multiplied by 0 is 0. And now let's move to the next, so we are done with Vm, let's move to the next point, which is Vb. So, and let me write here as a title electric potential. At B. So in order to determine the electric potential at B, we need to consider a voltage that we need to know a voltage that relates this point into another point in which we know the electric potential at that point. So simply we can consider the voltage UMB, which is equal to minus 8 volts. Notice that we are interested in determining the electric potential at the point B, which appears in this equation after writing UMB as Vm minus Vb, which is equal to minus 8. So notice that we are interested in determining Vb. The value of Vm is 0 minus Vb, which is equal to minus 8. So what's the type of this equation? This is a linear equation, one unknown. The unknown is Vb. So in this case, Vb is equal to 8 volts. Now we are done with Vb. Let's move to the next point, which is Va. We are interested in determining the electric potential at the point A. Then in order to determine the electric potential at the point A, we need to know a voltage that relates this point into another point such that we know the electric potential at that point. So let's consider the electric potential at the voltage UAB, which is equal to 4 volts. Now UAB can be written as VA minus VB, which is equal to 4, knowing that we are interested in determining VA. So VA minus VB, the value of VB is given by 8, which is equal to 4. What's the type of this equation? This is a linear equation, and one unknown, the unknown is VA. So VA in this case, dragging minus 8 to the right hand side, it will be plus, so 4 plus 8, which is equal to 12 volts. Then the electric potential at the point A is given by 12 volts. Then we are done with VA. Now as for VP, then similarly, in order to determine the electric potential at the point B, at the point P, we need to consider a voltage that relays this point into another point such that we know the electric potential at that point. Now if you consider the point A, notice that between the points P and A, we have a connecting wire. So we can say that Vp is equal to Va because we have a connecting wire, so the potential at the point B will be equal to the potential at the point A, and this is given by a connecting wire. And in this case, we have that Vp is equal to Va is equal to 12 volts, simply because the value of Va is given by 12 volts. Now in number 4, they are telling me an oscilloscope is connected across the terminals D and E of the lamp L4. So here when we connect the oscilloscope to the lamp L4, we have two choices. So either the phase terminal will be here and the mass terminal will be here, or the phase terminal will be here and the mass terminal will be here, and this depends on the measurement of the oscilloscope. You observe on the screen the luminous line is displaced downward. So because the luminous line is displaced downward, so the oscilloscope is measuring a negative voltage by 2 cm. So y, in this case the value of y is given by 2 cm, but notice that because it's displaced downward, so the value of y is negative, and this is equal to minus 2 centimeters. And the vertical sensitivity is given by 3 volts per centimeters. Then y is expressed in centimeters because simply the unit of SV is expressed in volts per centimeters. So this unit and this unit are always related to each other. Now in 4.1, they are telling me draw a figure showing the connection of the oscilloscope, knowing that UDE is positive. So first let me mention that since the luminous line is displaced downward, then the oscilloscope measures negative value. Now if UDE is positive, then we have that UED is negative y, because if UDE is positive, then we have that minus UED is positive, because I have flipped these two letters, then we will gain a minus sign. Multiplying this inequality by a minus sign, we know that this will change, then we have that UED is negative, and multiplying 0 by a minus sign, it will stay the same. And knowing that here in this case UED is negative, and here let me say, since the oscilloscope measures UED, then the phase terminal is connected to E, and the mass terminal is connected to D. Then this is the phase terminal connected to E, and this is the mass terminal connected to D. Now in 4.2 they are telling me to calculate the electric potential difference UED. So 4.2, now UED is being measured by the oscilloscope and we know the value, so here and we know the displacement of the luminous line in addition to the vertical sensitivity, then we can say that the voltage measured by the oscilloscope, which is given by UED, is equal to SV multiplied by Y. The value of SV is given by 3 and the value of Y is given by minus 2. Everything is expressed in the SI, so the value of UED is given by minus 6 volts. So UED is equal to minus 6 volts. And the same part they are telling me to deduce UCD, and by deduce it means that we need to use the previous part. In the previous part we have determined UED, then we can use it in order to determine the voltage UCD, and this can be done using the law of addition of voltages. Then always on the left we write the voltage that we are interested in calculating, which is UCD. And on the other side of this equation we go from C to D across different electric components such that we know the voltage across it. So we will directly go from C to B, B to M to E, and E back to D, knowing that we are interested in determining UCD. So now in the previous part we have determined UED. Notice that UED is essential in calculating UCD because it appears explicitly in the expression of UCD. Okay, for this reason they are telling me deduce. Now the value of UCB is given by 0 because across C and B we have a connecting wire, and here let me justify between brackets that UCB is equal to 0, and the reason is given by a connecting wire. As for UBM, knowing that UMB is equal to minus 8 volt, and in this case UBM is equal to plus 8 volts. Now across M and D we have a connecting wire, so let me say between the brackets that UME is equal to 0, and the reason given by connecting wire. So this is 0. And what about the voltage UED that we have calculated is given by minus 6. Plugging this on the calculator, then the value of UCD is given by 2. Everything previously is expressed in the SI, so UCD will be in the SI, which is volts. Now after we have determined this, let me place it here on the electric circuit that UCD is equal to 2 volts. And now in part 5 they are telling me an analog voltmeter with the scales 3 volts, 8 volts, 10 volts, and the DLD is equal to 100 divisions. Is connected across the terminals A and B of the lamp L1 such that it measures UAB. So notice that always the second letter is related to the COM terminal because the voltmeter, one of the terminals of the voltmeter is distinguished by the COM. The COM terminal is responsible for the negative and positive reading of the voltmeter. Now in 5.1 they are telling me draw the figure showing the connections of the voltmeter. So let me say here, since the first terminal is connected, since the COM terminal is connected to B, or let me say, since the voltmeter measures UAB, then the COM terminal is connected to B, and the other terminal is connected to A. And recall that the voltmeter is measuring the voltage across the lamp L1, so it must be connected to L1 in parallel. So this is the voltmeter. First here let me write that UAB is equal to 4 volts. This is the voltmeter like this, connected in parallel because according to law of uniqueness of voltages they have the same voltage. Now it's left to indicate the COM terminal. The COM terminal, as I mentioned here, it must be connected to B. So this is the COM terminal and this is the point B. Now in 5.2 they are telling me choose among these scales the most convenient one. In order to choose the most convenient scale, first let's write the definition of the convenient scale. The most convenient scale is the one having a value slightly greater than the one to be measured, Now in this case we are measuring the voltage UAB across the lamp, which is given by 4 volts. So the voltage that we are interested in measuring is 4 volts, so slightly greater than the one to be measured. Now referring to these scales, 3 volts is eliminated because it's less than 4. We are left with 8 and 10. The closest one is 8. So 8 volt is the most convenient scale. Now in 5.3, they are telling me calculate the deviation of the needle. After we have determined the convenient scale, and we know the capital D representing the dial, the voltage UAB of the voltmeter is related via the following formula to the scale, to D and capital D. Knowing that we are interested in determining D, so why I have labeled the voltage to UAB? Because simply the voltmeter is measuring UAB. Then let me flip this equation and write it in the following form. Knowing that we are interested in determining D, so dragging capital T to the right hand side, here it's divided and here it will be multiplied. Now dragging S, since we are interested in D, dragging S to the right hand side, here it's multiplied and here it will be divided. So D is equal to UAB multiplied by D divided by S. Now we are ready to calculate the value of D. The value of UAB is given by 4, the value of capital D is 100, and the value of S is given by 8. Now plugging this fraction on the calculator, then the value of D is given by 50, I think. Yes. Since everything previously is expressed in the SI, this, and this, so the value of D will be expressed in the SI, which is divisions. Then in this case, the deviation of the needle of the voltmeter is given by 50 divisions. Final exercise for this video is given by exercise number 12. In the circuit of the adjacent figure, the following voltages are measured. UBC is equal to 5 volts as usual. Voltage with its name, UBC, is equal to 5 volts. UAI, okay, so here, let me write that UAI is equal to 9 volts. UAD is equal to 2 volts. And UGD is equal to minus 2 volts. Number 1, calculate UAB. So, okay, let me make sure that I have labeled all the quantities. So we have UBC is equal to 5, UAI is equal to 9, UAD is equal to 2, and UG is equal to minus 2. Then we need to calculate the voltage UAB. So in order to calculate the voltage UAB, we need to consider a loop, or first let me write here apply law of additional voltages. So always on the left we write the voltage that we are interested in calculating, which is UAB, and on the other side of this equation we'll go from A to B across different electric components such that we know their voltages. So from A we can go to D, we know this voltage, from D to G, G to H, connecting wire, H to E, and E back to B. Okay, so A to D, D to G, G to H, and H to E, and E back to B. So this is a valid equation, started with A, ended with B, and each letter we have inserted it twice. UAD is equal to D given. Now if UGD is equal to minus 2, then UDG is equal to 2. Now what about UGH, UHE, UEB, all of them are connecting wires. So let me here write that UGH is equal to 0, UHE is equal to 0 and UEB is equal to 0, and for all of these the reason is given by a connecting wire. And this is equal to 4. Since all of these quantities are expressed in the SI, so the value of UAB will be in the SI, which is false. So UAB is equal to 4 volts. Now we need to calculate the voltage UEF. So let me write here apply law of addition of voltages. So we'll always write on the left the voltage that we are interested in calculating, which is UEF, and on the other side of this equation we'll write the voltages across different electric components going from E and ending with F. Then from E we can go to B, because this is a connecting wire. From B to C is given by 5, and C back to F, which is a connecting wire. Moreover, we could have done this way in another. We have calculated UEF in another method by simply saying law of uniqueness of voltages, because notice that E and F, B and C are in parallel because they have two terminals in common, E to B and F to C. So from E to B, B to C, and C back to F. So notice that UEB is equal to 0 justified. The value of UBC is given by 5, and the value of UCF is given by 0, and the reason is given by UCF is equal to 0. The reason is given by a connecting wire. So this is given by 5 volts. So UEF is equal to 5 volts. And let me label this voltage here. Now they are telling me UHI. So similarly, UHI can be calculated by going from H to E, E to F, F back to I, but here let me say by law of uniqueness of voltages. Okay, here I don't know the names of the electric components, so we cannot refer to them. So let's use the law of addition of voltages. Apply law of addition of voltages. So I wanted to calculate UHI using the law of addition of voltages, but first I wanted to mention that this component is in parallel with this component, but I don't know the names of this components. So in a more better way, let's say law of addition of voltages, then UHI is equal to UHE plus UEF plus UFI. So this is 0 justified previously. UAF is 5, and UFJ is given by 0, and the reason is that UFJ is equal to 0, it's connecting wire. So this is equal to 5 volts. Now we are done with these. We need to determine the voltage UEH. So why they are asking me about UEH, I don't know. This is 0. Let's not discuss it, because we have already mentioned that UEH is equal to 0. Now what about UDE? So UDE is interesting. Notice that across D and E we don't have any electric component, but this doesn't mean that we cannot calculate this voltage. So let's say apply law of addition of voltages. Then UDE, from D we will go to A to B, and B to E, and everything is justified. Notice that you have started with D, ended with E, and each letter we have inserted it twice. UDA is given by, if UAD is 2, then UDA is minus 2, plus UAB, which is 4, and this is 0 justified, so this is given by 2 volts. Now as for UGB, then from G to B, notice that across G and B we don't have any electric component, but this doesn't mean that we cannot calculate the electric potential difference. We can go from G to D, from D to A, from A back to B. UGD is given by -2. If UAD is 2, then UDA is -2, and UAB is given by 4, so this is equal to 0. Okay, so UGB is equal to 0. It happens sometimes that the potential between 2 points is said to be 0. Okay, now let me make it clear. If between G and B we have a connecting wire, then for sure that UGB is equal to 0. But this doesn't mean that if UGB is equal to 0, then across G and B we have a connecting wire. Okay, so the implication here doesn't hold. Okay, so if we have a connecting wire, then the voltage is 0. But this doesn't mean if the voltage is 0, then we have a connecting wire. And this, as an example on this, for an ammeter, we have an ammeter which is not a wire, and the voltage across it is 0. Okay. So this later we will see in chapter 4 using Ohm's law. If U is equal to 0 and U is equal to R multiplied by R, so this is 0, then this is 0 is due to two reasons. Either R is equal to 0 or I is equal to 0. Okay, so the 0 voltage comes from two factors. Either the resistance is 0 or the current is 0. So here, because you don't have an electric component between G and B, the reason behind this potential difference is 0 is due to the current. Okay, so we are done with the UGB. Now finally UBH. So no need to justify UBH because, okay, let me say it, apply law of addition of voltages. So UBH is eventually given by UBE plus UEH. Both of them are electric wires, connecting wires, so this is 0. And also UBH is equal to 0, justified, it's a connecting wire. Now this is it for number 1. Now in number 2 they are telling me which terminal A or B has a higher potential. So in order to know whether A or B has a higher potential, we need to consider the voltage UAB. So the voltage UAB is given by 4 volts, which stands for VA minus VB is equal to 4, which is a positive number. So VA minus VB is positive, which means that VA is greater than VB. So this is an inequality between the points A and B. So let's say since VA is greater than VB, then A has a higher potential compared, this is important, very important, compared to B. Now in 2.2, which terminal E or F has a higher potential? So we need to consider the voltage UEF, which is given by 5 volts. UEF is given by VE minus VF, which is equal to 5, which is a positive number, which means that VE minus VF is positive. So this is an inequality between VE and VF. So VE is greater than VF. So since VE is greater than VF, then E has a higher potential compared to F. So this is it for part 2.2. Now in number 3, specify the positive and the negative poles of the source. So we need to know whether, so the source has two poles, and they are given by A and C. So in order to specify whether which one of these is the positive pole and the negative pole, we need to consider the voltage UAC. Why? Because if we consider any DC voltage source, so we know that if we are talking about the potentials, okay, if this is the point P and this is the point N, so if UPN is positive, so UPN is positive because we are measuring from positive to negative. So first let's determine the voltage of the source, which is UAC. If UAC is set to be positive, then this is the positive pole and this is the negative pole. If UAC is negative, then this is, so which means that UCA is positive, so this is the positive pole and this is the negative pole. So let me repeat here. In order to know which of these poles corresponding to the source they are given by A and C is the positive and the negative, we need to determine the voltage UAC. If UAC is positive, then A is the positive pole and C is the negative pole. However, if UCA is positive, then C is the positive pole and A is the negative pole. All of this counts on the sign of the voltage between the two poles of the source. So let's calculate the voltage UAC, and this can be done using the law of addition of voltages. So apply law of addition of voltages. So UAC is simply given by UAB plus UBC, which is equal to 4 plus 5, and this is given by 9 volts. So UAC is equal to 9 volts. So since UAC is equal to a 9 volts, which is a positive number, then A represents the positive pole and C represents the negative pole. Now in part 4, they are telling me show on the diagram the connection of the voltmeter to measure the voltage UEI. So we are using the voltmeter to measure the voltage UEI, which is across these 2 points. So this is the voltmeter. So one of the terminals connected to E and the other terminal is connected to I. Let me make it better. But now we need to represent the COM terminal. The COM terminal is always related to the second point in the voltage, so the COM terminal must be represented here. And let's justify and say, since the voltmeter measures UEI, then the COM terminal is connected to I, and the other terminal, this is I, okay, and the other terminal is connected back to E. Now in part 5, they are telling me that if point E is taken as a reference, as an electric potential reference, so this is the electric potential reference, we are interested in determining the potentials of the points C and G. So first let's justify and say, since our electric potential at point E, because this is our reference starting point, electric potential reference, electric potential at E. Since E is taken as an electric potential reference, then we have that the potential, the electric potential at the point E is equal to 0. Okay. Let me make some space here. So now we are interested in determining the electric potential at the point C. Let's start by the point C. So in order to determine the electric potential at the point C, we need to know the voltage that relates this point to another point such that we know the electric potential at the other point. So the closest points to the point C are given by the point B and the point F. However, we don't know the electric potential at the point F, so we cannot consider this point. So we can consider the point B. Why? Because B and E have the same electric potential, which is 0, because E is taken as a reference electric potential. So first, let's justify that VB is equal to VE, or let me say as a title, electric potential at C. So the voltage that we are interested in, we need to consider is UBC, which is equal to 5 volts. And this is given by VB minus VC, which is equal to 5, knowing that we are interested in determining VC. So now in this case, this is a linear equation, two unknowns, VB and VC. In order to determine VC, we need first to know VB. But here we can say that VB is equal to VE, and the reason is given by a connecting wire. The value of V is given by 0. So this is 0 minus VC, which is equal to 5. Now this equation is a linear equation, and one unknown, the unknown is VC, so VC is equal to minus 5 volts. And now for the other point, the point G, electric potential at G So in order to determine the electric potential at G, we need to consider a voltage such that we know this voltage and that relates this voltage to another point such that we know the electric potential at that point. However, in this case, notice that between G and H we have a connecting wire, between H and D we have a connecting wire. So in this case, this potential is equal to this potential and this potential is equal to that potential. So let's say that VG is equal to VH, connecting wire, and VH is equal to VE, the reason is given by connecting wire. So VH is equal to VE, the reason is given by connecting wire. So notice that in this case, if VG is equal to VH and VH is equal to VE, then we can say by comparison that VG is equal to VE. But we know that the value of VE is equal to 0, so VG is also equal to 0. We could have simply said that VG is equal to VE, and the reason is given by a connecting wire, because simply between G and E we have a connecting wire. Okay, or another way to solve it, simply we could have said that VG is equal to VE, so VG is equal to 0, and the reason is given by a connecting wire. So that's it for me in this video, guys. In the next part, part 5, we will complete the explanation of this chapter.